In this video, we will learn how to calculate an overall heat transfer coefficient in production or injection wells. During well flow, the heat is usually transferred from and throughout tubing, annulus, casing, and cement to rock formation. Each of these media have individual thermal properties and make the process of heat transmission prediction very complex. Often for analytical solutions to temperature modeling, two types of radial heat flow are considered steady-state and transient. Steady-state heat transfer delta Q1 occurs within wellbore. It is expressed as 2 pi multiplied by tubing radius RTI by U value by delta T, which is a difference between tubing temperature and the outer boundary of the wellbore. Transient heat transfer delta Q2 occurs from wellbore to formation. It is expressed as 2 pi multiplied by Kf, which is formation thermal conductivity, delta T, which is the difference between wellbore and the formation temperature, and divided by Ft. In this case, time function Ft is a solution of the diffusivity equation. Okay, finally, delta Qt equals to delta Q1 plus delta Q2, which is the total heat transfer from the wellbore. Now, let's look more closely at the U value in the first formula, which is also called a steady-state overall heat transfer coefficient. For this purpose, we will consider a well, a gas production well, where we see a typical production string with tubing pipe and casing and cement around the casing inside a drill hole. We will follow the procedure to calculate a U value. The U value is given by a formula of the sum of local heat transfer coefficients, where HTconv is local heat transfer coefficient for inside of tubing forced convection. HTcont is for conduction through the tubing material. HCconv is for free convection between tubing in and casing, which is annulus. HCcont is for conduction through the casing material. And finally, HCemcont again due to conduction but through cement. Now we will examine individual expressions for these various local heat transfer coefficients. So, HTconv for inside tubing forced convection will be equal to a constant multiplied by average fluid conductivity, gas in our case, Reynolds and Prandtl numbers over RTI, which is a mean inner radius of tubing. To calculate fluid conductivity, dimensionless Reynolds and Prandtl numbers, we need to know flowing fluid composition and properties. The next additive to the overall U value is a local heat transfer coefficient for tubing conduction that can be written as K, which is thermal conductivity of tubing steel, over RTI multiplied by natural logarithm of RTO over RTI, which are outer and inner radiuses of tubing. It is obvious that it will greatly depend on pure conductivity of the pipe material and its dimensions. The third item is a local heat transfer coefficient due to free annulus convection between tubing and casing. It will be equal to a constant multiplied by Greshov and Prandtl numbers, casing fluid conductivity over RTI multiplied by natural logarithm of RCO over RCI. Note, if Nusselt number, which is a group of parameters in the numerator, of the formula equals to 1, then annulus convection becomes a pure equivalent to annulus conduction. We well know that one of the best natural heat conductors is water, and one of the worst is air or gas. So if we have gas filled annulus, then we put a good resistance to heat loss and keep flowing upstream gas warm. Okay, the rest of the local heat transfer coefficients due to conduction of casing and cement can be written similar as the tubing thermal resistant ones. We press Calculate button to perform calculations. As soon as the calculations are completed, we can drag and drop the resulted log to the logs panel and analyze it. We see that the heat transfer coefficient log is not constant over the length of the wellbore, but greatly depends on flow rate, fluid properties, and the well sketch. I will do some curve filling for the log. Okay, we see the minimum heat loss at the bottom of the wellbore, where no flow occurs. It tends to 0. While the flow rate increases upwards, the heat transfer will reach its maximum. Then, further upstream where annulus exists, it provides a better constant resistance to heat flow from wellbore, and the U value decreases to around 6 joules. Right, at the end I would like to stress a few important points about the U value parameter calculation. We have to use database for typical formation, fluid and wellbore material conductivities for calculation of U value. We have to tune overall heat transfer coefficient to match recorded flowing temperature log, which is a blue one on our middle track. Care should be taken while tuning individual components of U value. It's not recommended if all other components are not fully understood. Okay, we have finished with overall heat transfer in wellbores. Visit our website to learn more about production logging and wellbore analysis.